We're now going to look at the rays involved using a concave lens. Now, a concave lens is a diverging device. So by diverging, we mean that any parallel ray that passes through this lens will not converge through the focal point, but will diverge away in line with this back focal point. So these types of optical devices are said to have virtual focal points. Now, I've already pre-done the diagram. So you can see that I've labeled my two focal points at the 3 centimeter mark. They would be negative focal points because this is a diverging lens. And again, every 4 squares represents 1 centimeter on my graph paper. My object is drawn at the 4 centimeter mark, upright as usual, and large enough so that the rays that I'm drawing off of it don't get all cluttered. So I'm ready to go. Now once again, I want to start my diagram with a parallel ray, parallel to our principal axis, that strikes the lens and goes through the focal point. But it kind of behaves a little bit differently when you're talking about a concave lens. The focal point is actually virtual, it's on the left. So let's draw that first ray in and discuss. So here's my first parallel ray. Once it strikes the dead center of this lens, it diverges along this line. And notice this isn't just any random angle. I've taken my ruler and I've lined it up with this back focal point. So this is the actual ray on the right hand side. This is my actual refracted ray, and it is lined up with this back focal point. So that's why I've got these dotted lines. That's not the actual ray, that's just where it appears to be coming from virtually. So the next ray we're going to draw, just like the previous lenses, is a ray that goes straight through the center of the lens undeflected. So here's my second ray, straight through the dead center of our lens, and it does not deflect at all. Now it's always the two refracted rays that must cross, and for this style of lens, anything diverging, they'll never cross on the real side. It's always going to create a virtual image. So these two rays, if we're standing on this side of the lens, will appear to cross behind the lens where the two lines intersect. So we dot this one back, it's already done for us, and if I take this other refracted ray and I follow it back, it appears to intersect with that top ray right where my hand is. Now before we draw in our image, there's one more ray we can draw, and that's a ray that's associated with this far focal point. So we're going to start a ray in line with this far focal point, and once it hits the lens it'll go parallel. Let's draw that one now. So this is my third and final ray, a ray that is in line with this far focal point, and you'll see this light blue line here to show you how I lined up my ruler. Once it hits the center of the lens, it'll refract so that it's parallel. Now this one can be a little bit confusing, so just make sure it makes sense in reverse. If I have a parallel ray coming from the right towards the left, it will diverge away from the lens so that it's in line with the back focal point. So it makes sense. Now these three rays all must converge. So the top one and the bottom one, we see they converge over where my hand is. We want to ensure that this third ray also converges where that hand is. So if I dot this ray back, let's see where we're at. So as expected, we see that they all appear to converge behind the lens on the same side of the lens as the object, right where my hand is. And so these three rays are not actually at this point, they only appear to be at this point, so we call this a virtual image. Let's draw in our image now and summarize. So here we see my virtual upright image. It's located beyond the 1.5 centimeter mark and before the 1.75 centimeter mark. So a good estimate would be about 1.71. And because it's a virtual image, we say that the image distance is negative 1.71. So the image distance is negative 1.71 centimeters. It's upright, it's virtual, and we can see that it's smaller than the original object.